This is a demonstration of the TAAC-1 Visualization Accelerator, a two-board add-on for a sun-side workstation that performs image processing, volume rendering, interactive graphics, and photorealistic rendering. I'm going to be demonstrating a number of the capabilities of the TAAC-1, and everything that you'll be seeing on this videotape will be occurring in real time unless we say otherwise. The first part of the demonstration will be graphics, both interactive graphics and photorealistic rendering. We'll then go on to image processing, volume rendering, and finally show some terrain mapping. This first demonstration is a program called Flex that was developed by Mike Peak at Scripps Clinic for interactive display of complex proteins. This is a protein called superoxide dismutase. Notice it's being rendered with anti-alias, depth-cued, Z-buffered lines. You can see the difference between these lines and non-anti-alias lines with the jaggies that people are used to seeing on rastered displays. The TAAC-1 has the capability of drawing lines in a number of different ways. Because the TAAC-1 is fully programmable, you can write functions for rendering objects in many different ways, and so among the different rendering styles you find in the TAAC-1 graphics library are a sphere primitive. These are real spheres, one at each atom location, along with lines for the atomic bonds. We can also do full space-filling model, a CPK model of the molecule. These are done with what are called Z-blits, or Z-buffered blits of sphere templates, but because they're Z-buffered, you'll notice that you get correct interpenetration of these spheres. It's quite uncommon to be able to do spheres interactively. And yet another technique for rendering this molecule is what's called the ribbon model, which indicates the backbone or the main chain of the protein. These are done simply with smooth shaded triangles. Along with these different rendering techniques, the TAAC-1 is also extremely fast at computation, so one of the things we can add to this model is various normal modes of motion that were calculated by Dave Case at Scripps Clinic. So I've turned on one of these high frequency modes, and on every update the TAAC-1 is now recalculating the position of every atom according to which of these modes is turned on and what the temperature is. So if I increase the temperature, it will increase the vibration, or if I decrease the temperature, it will slow it down. The vibration has been exaggerated here for demonstration purposes. If I turn on a number of these, we can see the motion more closely resembles molecular dynamics. This program also works in stereo. I'll just demonstrate that, though, without a stereo plate in front of it. All you will see is multiple lines to both the left and the right image. Next, I'm going to bring up a program we call Quick View, which is your traditional interactive polygon rendering program with the traditional data sets of Volkswagen and Space Shuttle, etc. Scale this up a little bit. Here we're rendering it as wireframe. We can render it with Gaussian shaded polygons, different colors, different backgrounds. Move the light source around. So here you can see the basic interactive graphics capability of the TAAC. All of these two programs were done using the graphics library that comes with the TAAC-1. This next program that I'm bringing up is a demonstration of the ART package, that is the Advanced Rendering Toolkit that comes with the TAAC-1. This is for photorealistic rendering. It's a script-controlled rendering program that does very high-quality rendering techniques, including texture mapping for marble, environment mapping. We'll see translucent windows, reflectance mapping for reflections in the body of the car that will be rendered here. This data set has about 40,000 polygons in it, and it's being rendered as we watch. You'll notice that in this particular demonstration we are not doing anti-aliasing of the car, and so you will see jaggies, rough edges along the various polygons. The program, the toolkit does provide anti-aliasing through stochastic supersampling, and when this image is done I'll bring up the final rendered version with anti-aliasing, which was done with 8 passes to do the supersampling, and gives you a much smoother final image. Here we see Phong shading. You can see the reflection of the environment map in the body of the car. And the translucent windshields. Okay, that's finished. I'm going to quit that program and bring up a separate program just for loading already calculated images, so that you can see the final anti-aliased version of that, as well as some other images rendered with ART. So this is the same jaggy version we were looking at a moment ago. Now I'm going to load up the anti-aliased version, and you'll see the difference. You can see how the polygons are now smooth, the edges are clean, there aren't those little alias holes that you saw in the previous version. And this took, as I said, 8 times longer than the previous rendering we just saw. Here are a couple other examples of images done using ART. In this case, the words TAAC-1 were done with a bump map. This is actually a single smooth polygon, but the indentation is done by using a bump map. Next, I'm going to move on to image processing. The TAAC comes with 2 complete image processing libraries. One callable from TAAC-1 programs, another called the host callable image processing library, is a set of functions written to be device independent and callable from Sun programs. So one need not program the TAAC at all, rather one can write a standard Sun program and then call the host callable image processing library functions for doing image processing on the TAAC from the Sun program. Here I've loaded a 16-bit image, and the first function I'm going to do is adaptive histogram equalization, which is a contrast enhancement technique. Here you can see the greatly enhanced contrast within various parts of that image. AHE is done by doing multiple histograms across the image, tiling it, doing histogram equalization within each of those tiles, and then interpolating between those different regions to get the final pixel values. One can also, this is in particular contrast limited AHE, which means you can set a limit as to the number of pixels having a particular value. If I reduce that clip limit, what we'll see is it'll reduce some of the noise in the final version and still keep a great deal of that contrast. The other thing we can do in this particular demonstration is traditional intensity windowing. Here I'm reducing the window to a much smaller window of about 200, and now I can move that window around. You can see the grayscale on the left of the image showing you where the window is located. You'll note here that we do intensity windowing differently than most traditional image processing devices. We are not doing a video lookup. You'll notice that the image on the right stays the same, whereas we're clearly changing the lookup for the window on the left. The way we do intensity windowing is by storing the original image someplace in the frame buffer, reading the image, doing a lookup in our programmable lookup table, and then writing a new image out elsewhere in the frame buffer, and that's what's being displayed on the left of the screen. So this gives you a good idea of how fast the TAAC can read, process, and display an image. We can also use different color maps. This is a color map, a heated object color map, pseudocolor, etc. This next demonstration goes through many of the families in the TAAC-1 image processing library. These families are listed up here: arithmetic and logical functions, miscellaneous functions, Fourier domain filtering, spatial domain filtering, remapping functions, morphological functions, and various others. I'll run through a number of these. This demonstration is set up to have 4 different parts of the frame buffer where we can store images. These are 0 and 1 here, and this is 2 and 3. You'll notice these are the images that were left in the frame buffer previously. Right now we're interpreting what's in the frame buffer as full color, but we can look at any individual 8-bit channel of the front 24 bits, the least significant 24 bits of the frame buffer. It's a 32-bit deep frame buffer. So these are really grayscale images, for example, and so we'll just look at the red channel, or the least significant 8 bits. I'm going to load up an 8-bit image and perform some of the functions from the image processing library. I'll start with some simple functions like a bit shift. So here we shifted this image 1 bit. Another function in the miscellaneous functions is a 3D projection, which creates a wireframe mesh with height as a function of intensity. And notice you can change various parameters such as the azimuth of that image created. All of this again is being done in real time. Now we're going to go to interactive Fourier processing. Here I'm going to create a 128 squared box, and as I move this box around, the TAAC-1 is doing a 2D floating point FFT on the contents of that box and displaying the power spectrum on the right side of the screen. We can also, if we like, not just display the power spectrum, but do filter and then an inverse FFT. Let's do a high-pass filter. We have to reduce the frequency there of the filter and increase the gain. And so now when we move this box around, we're doing 128 squared FFT, high-pass filter, and inverse FFT on the fly. If we like, we can go ahead and do the full 512 squared FFT, high-pass filter, and inverse FFT. Takes about 3 seconds to do a 512 squared FFT, and so this total operation will take roughly 7 seconds. We also have spatial domain filtering. I'm going to load up a different image for this. This is a image retraced on the TAAC, and we'll do a Gaussian filter on it. So we've now smoothed out some of the edges. Now we'll go to the arithmetic functions, which we skipped earlier. Subtract these 2 images, and we can see the difference between the images is indeed the edges at this point.